This lecture is part of an online course on rings and modules, and we'll be giving a few examples of rings related to groups. In particular, we'll be looking at the group ring of a group G. So this is going to give us a functor from groups to rings. So for any group we construct a ring, and homomorphisms of groups correspond to homomorphisms of rings. So the construction of the group ring is fairly easy. What we do is we take we take the elements of the group to be G0, G1, G2 and so on, and we take the group ring to be a sum of copies of Z for each element of the group. So we can think of this as being ZG0 plus ZG1 and so on. So the elements are just formally linear combinations of elements of the group G. And addition is kind of obvious, and multiplication is kind of obvious too, because we define GIGJ to be GIGJ. So here this is the ring multiplication and this is the group multiplication, so we're just doing the obvious thing and saying you multiply elements in the ring in the same way that you multiply them in the group. Actually, it's useful to have a variation of this where instead of working over the integer Z, we work over some other ring R, usually commutative, and we take the group ring of G, so the group algebra of G, over R to be just a sum of copies of R for each element of the group G, and we just define the product just like that. And I should say here that an R algebra is just a ring S with a homomorphism of rings from R to S. Often we assume R is commutative and its image commutes with S. So for example, any ring is just a Z algebra because it can be made, there's an obvious homomorphism of rings from Z to the ring. And it turns out to be useful to have this sort of relative construction where instead of working over the integers, you work over some sort of base ring R. For example, R might be a field, and in field theory it's useful to work over a base field rather than just look at a field by itself. So let's see an example of this. So suppose we take the group G to be the Klein 4 group. So it has 4 elements, 1, A, B, C, with A squared equals B squared equals C squared equals 1, A, B equals C, and so on. And what I want to do is to look at the group ring of this group over the complex numbers. And this group actually splits as a product of 4 rings. Well, it certainly splits as a product of 4 vector spaces because you can write it as C plus CA plus CB plus CC. However, this is not a product of rings because the complex multiples of A certainly don't form a ring, at least not a subring. So writing it as a product of 4 rings is a little bit more complicated. So first of all, we need to see how to write a ring as a product of 2 other rings. So suppose I've got a ring that's a product of S and T. In other words, its elements are just the form pairs of elements with S in the ring S and T in the ring T. Well, what we do is we notice that the elements U, which is 1, 0, and 1 minus U, which is 0, 1, because the element 1 in the ring is just equal to 1, 1. These have the following property. First of all, U commutes with all elements of R. In other words, UR equals RU. And secondly, U squared is equal to U. So things with this property are called idempotents. So if a ring splits as a product, then we can find an idempotent that commutes with everything in the ring. Conversely, if we've got U, then we can reconstruct R as a product of two rings, and we just put S equals UR and T equals U times, 1 minus U times R. It doesn't matter whether you put R on the left or the right because U is in the centre. And then you can see, for example, that anything in the ring can be written as a sum of things in S and T, because R is equal to R of U plus R times 1 minus U. And conversely, if U times R1 is equal to 1 minus U times R2, so if you've got something that's in S and in T, then multiplying both sides by U, we find U R1 equals U squared R1, because U is idempotent, which is equal to U minus U times R2, again because R is idempotent, which is 0. So U R1 must be 0 and 1 minus U R2 must be 0. So R splits as a product of two rings. So in order to write this group ring as a product of rings, we want to find idempotents. And one easy way to do is to just write them down explicitly. So here's an idempotent, 1 plus A plus B plus C divided by 4. Here's another, 1 plus A minus B minus C over 4. And here's another, 1 minus A plus B minus C over 4. And there's another obvious one, 1 minus A, where have I got to? Minus B plus C over 4. So if I write these as U1, U2, U3 and U4, we've got lots of idempotents. So Ui squared is equal to 1, and we notice Ui Uj equals 0 for I not equal to j. So we've got loads of idempotents, and the group ring C of G splits as a sum or a product of four rings, just of CU1 times CU2 times CU3 times CU4. So, the group ring of a ring splits in a not completely obvious way as a product of four rings. This is actually true for the group algebra of any finite group. What we do is we find the group algebra of any finite group is a product of, well, they're actually matrix rings over the complex numbers. So in this case we had all the ni's are 1, so we just have 1 by 1 matrix rings. And in general, any group algebra of a finite group splits like this, where the ni's turn out to be things called the dimensions of the irreducible representations of the group. I've got some lectures on representations of finite groups if you want to find out more about this. Also, you notice in this, we don't really need G to be a group. We never use the inverse of G. We can take G to be a monoid, which is kind of like a group without inverses. So it's got an identity element and the product is associative. So let's have some examples of this. First of all, let's just take G to be the positive integers under addition. Then you can see the group ring of G over some ring is just the same as the ring of polynomials over X, because the monomials x to the 0, x to the 1, x to the 2 and so on kind of correspond to the elements 0, 1, 2 of G, because x to the I, x to the j is equal to x to the I plus j. So this is just the addition of the positive integers. If you want to take G to be all integers, then the group ring R of G is in much the same way just the ring of Laurent polynomials, where we allow inverse powers of x. So this turns up in complex analysis a fair amount. Suppose we take G to be the positive integers without 0, and instead of doing them under addition, we now do them under multiplication. What does the group ring look like? Well, what we get are what is called the formal Dirichlet polynomials. So here we think of the elements of R of G as being things of the form r1 over 1 to the s plus r2 over 2 to the s plus r3 over 3 to the s and so on. And we don't think of 1 over 1 to the s and 1 over 2 to the s as really being functions or anything. They're just sort of formal placeholders which makes remembering the multiplication easier. The point is that 1 over m to the s times 1 over n to the s is at least formally equal to 1 over m times n to the s. Of course, if R is the ring of complex numbers, then you can think of these as being functions on the complex numbers, but you don't really need them to be functions. So you should distinguish between Dirichlet series and polynomials. So here we're multiplying these by adding the exponents. Here we're multiplying these by multiplying the well, these aren't the exponents, whatever the thing that isn't the exponent is called. Well, just as for polynomials, there's a variation of polynomials where you look at formal power series. So the formal power series ring over a ring is sometimes indicated by putting double brackets, and you think of this as being all formal series that go on forever. So we have a possibly infinite number of non-zero coefficients. And you can multiply and add these in pretty much the same way that you do for polynomials, except you get an infinitely long power series instead of a finite polynomial. And you can do the same for formal Dirichlet series. Where we take a0 over 1 to the s, sorry, a1 over 1 to the s plus a2 over 2 to the s and so on, and we allow an infinite number of the ai's to be non-zero elements of our ring R. And when we take R to be the complex numbers, of course, you can think of them as being possibly convergent Dirichlet series. For instance, there's the famous Riemann Zeta function, which is 1 over 1 to the s plus 1 over 2 to the s and so on. And there's this inverse, let's write it as m of s, which is going to be mu of 1 over 1 to the s plus mu of 2 over 2 to the s and so on. So what's mu of n? Well, if you've been to a number theory course, you know that mu of n is equal to 0 if n is divisible by the square of a prime, and it's equal to plus or minus 1 if n is a product of an even or odd number of distinct primes. And now m of s actually turns out to be the inverse of zeta of s. So m, you can write m times s is equal to 1 in the ring of formal Dirichlet series over a ring. And this identity here turns out to be equivalent to the following identity. If you take sum over d divides an integer n of mu of d, then this is equal to 1 if n is equal to 1 and 0 if n is greater than 1. This can be taken as almost a defining property of mu, if you like, and you can then work out that mu is given like that. So relations in this ring of formal Dirichlet series encode various number theoretic relations. This is a particularly simple example of one, and in a course on number theory you can probably see lots of others. So the group ring is actually an example of a joint functor. So there's a functor from, let's look at the category of R algebras and the category of groups. And there's an obvious functor from the category of R algebras which takes an R algebra S to the invertible elements. And you can think of this as being a forgetful functor. We're sort of forgetting about the addition and we're forgetting about the non-invertible elements. And you can go back in the other direction. You can take a group G to the group ring R of G. And this is an example of a left adjoint functor. So you may remember from the lectures on category theory that this means that the group homomorphisms from G to the invertible elements of a ring correspond to the ring homomorphisms from the group ring to that ring, and this is more or less obvious. So we can think of this functor as a sort of left adjoint to this forgetful functor, which is the right adjoint functor. Remember, saying there adjoint is just saying that these two sets are naturally isomorphic. So the group ring, you can also think of this as being in some sense the R algebra freely generated by the group G, where when you're generating something by the group G, you obviously want to preserve the group multiplication. Another variation is that we can take the free R algebra generated by some set, say it consists of elements A, B, C, and so on. So here I'm going to take R algebras to have R in the centre of the R algebra. I don't want to worry about funny R algebras with R possibly not commuting with things. And to construct this, what we can do is we can just take the free monoid on A, B, C, and so on. So let's call this monoid G. This means that G has elements 1, A, B, C, A squared, A, B, B, A, B squared, A, C, and so on. So they're all monomials in A, B, and C, and so on, except that you have to keep track of the order because these don't commute. And then the monoid ring of this is just going to be the free R algebra generated by A, B, and C, and that's kind of fairly obvious if you think about it a bit. That's the free non-commutative R algebra. In the commutative case, instead of taking the free monoid on A, B, and C, we take the free commutative monoid, whose elements are things like 1, A, B, C, A squared, A, B, B squared, and now this is actually equal to BA, and this is just giving us a polynomial ring. So the polynomial ring is just, of course, the free commutative algebra over a ring generated by various elements. There's another way to think of the ring of Laurent polynomials. So a Laurent polynomial is just a map from Z to the complex numbers, which is 0 for almost all Z. So what we're doing is we're just, if we've got a Laurent polynomial sum of a n z to the n, you can think of that this as just being the map which takes n to the coefficient a n. Well, if you do this, the multiplication in the ring can be defined as follows. Suppose you've got two functions, f and g, from z to c. Then the convolution of f and g is the function which takes n to the sum over m of f of m, g of n minus m. If you think about it, this is just the usual rule for multiplying polynomials, except I've written it in a slightly funny form. So I'm thinking of polynomials as being functions from z to the complex numbers rather than as formal expressions like this. So what's the point of doing this? Well, this is called the convolution, which seems to be a funny way of talking about multiplication of polynomials. However, what we can do is we can change z to the reals. And now I'm going to look at functions f and g from the reals to the complex numbers, and I'm going to say that these have compact support. And I'm now going to try and define the group ring in the same way, except I'm going to take the topology into account, and instead of saying these functions have finite support, I'm going to say they have compact support and are continuous. And then I'm going to define the multiplication in the same way, f star g of x. Well, I can't sum over things because, you know, these functions are non-zero for an infinite number of values, but summation is more or less the same as integration. So I'm going to integrate over y of f of y g of x minus y dy. So this is also called the convolution of two functions. So you can think of the convolution of functions as being a sort of version of the group ring. You're sort of taking the group ring of the reals, except you're allowing an infinite number of non-zero coefficients in some sense, and you're also insisting that the coefficient should be a continuous function of something. And you can then check that this does actually give you a perfectly well-defined ring. Well, when I say a ring, I should of course mean a ring with no identity element, because an identity element for this ring would have to be a function that had support just at 0 and has integral 1. And of course there are no functions whose support is a single point which have integral 1. So you can't actually find an identity in this ring. Of course you can mess around with things like the Dirac delta function, which has this property. Well, the delta function isn't actually a function, it's a measure. And you can do this, you can define convolution of measures in the same way, and you can make suitable measures into a ring provided you add some sort of integrability condition to them. Finally, we can actually give a nice example of a homomorphism of rings. One example of a homomorphism of rings is the Fourier transform. So you remember in analysis there's something like a Fourier transform which optonormalization is defined by f of x is the integral from minus infinity to infinity of e to the I xy dy times f of y, I suppose. And there should be a factor of 2 pi that goes in there somewhere, but there are several different conventions for this, so I'm not going to worry about this too much. And then you find that under suitable conditions, the Fourier transform of f and g is the convolution of the Fourier transforms of f and g. Of course, to make this work, you need to put in some sort of condition on f to make sure that all the integrals converge and so on. And if you look at this, it's just saying the Fourier transform is more or less a homomorphism of rings from a ring of continuous functions under pointwise multiplication to some ring of continuous functions under convolution. Except in both of these cases I should add some sort of you need to add some sort of conditions to make sure the integrals converge. And there are various different ways of doing that, and analysts get very excited about all these different possibilities, but this is an algebra course, so I'm not going to worry about it. So the Fourier transform is a homomorphism of rings taking multiplication to convolution, and for that matter it also takes convolution back to multiplication. Okay, next lecture we'll be doing some more miscellaneous examples of rings.